Talk today is local partitioning and hidden cliques in massive graphs. Please welcome Professor Yuval.
Thank you very much. It's a pleasure to be here. And so I'll be describing today two works on different but related subjects. The first is joint with Reed Anderson, and the second with Yael Dekel and Ori Gurel-Gurevich. And so let me maybe start. I'll come back to this picture, but one of our goals will be to describe what the algorithm you see here is doing. So it's trying to find sets in this graph which form communities, so meaning that the number of edges connecting the set to the outside is small compared to the number of edges inside. I'll come back to these pictures when we have some relevant definitions. So let me start with the work with Reed Anderson. So the problem here involves you have a huge graph. You want to find a suitable small set of it where the number of edges connecting to the outside is relatively small to the inside. And what is interesting for me is that the algorithm emerged from an earlier completely theoretical work on mixing times of Markov chains that I did with Ben Morris. Anyway, let me start with this kind of applied motivation for this type of problems, where we have large graphs, and this number is outdated now. We have a trillion nodes in this kind of graph. So we have graphs with at least tens of millions, usually hundreds of millions or many billions of nodes. And in these graphs, we want to do partitioning, and in particular, we see local partitioning. Now, in the pictures, I won't show these graphs because they're very hard to visualize, and we'll just use, for illustration, a random geometric graph. So this is a graph obtained by just throwing points down at random or according to Poisson process, and then connecting those that are closer than some threshold. The graphs we can see are much, much smaller than the graphs we really want to analyze, so keep that in mind. So we'll be looking for sparse cuts, and I'll come back to the motivation, but just for the formal definition, given a set S, we compare the volume of S, namely the total number of edges, or the sum of the degrees of the vertices in S, and we compare that to the number of edges that connect S to the outside. So this ratio, number of S's to the outside divided by the sum of the degrees, is sometimes called the conductance or the expansion constant or the Chigger constant. It's important, so it has many different names, and we can recognize some kind of community by finding a set where this number is very small. So this would be a set where there are lots of interconnections inside, relatively few to the outside. So the problem of graph partitioning and algorithms for it is, this is a very big subject, and usually it's considered in the context of global graph partitioning. We see the whole graph, we want to cut it into pieces, and this is used in many areas, in particular when we are running search algorithms on something, a graph of the order of the web. We would take this graph, put it on the RAMs of several thousand computers, and then we want to run the algorithm on this combination. So we want most of the work to be done inside one RAM rather than communicating, moving from one computer to the other. So when we partition the web to put it onto these computers, we want to do it in such a way that minimizes these edges going across different parts. The problem of partitioning is not going to be the main thing we're talking about here, but rather local partitioning. So how is that different? In local partitioning is more targeted. So we think of this really huge graph with a trillion nodes, But now suppose I'm not doing the step of partitioning the whole graph. I'm just interested in a particular node, say a particular website, and I want to know something about a small community of this website. Which are the somehow 5,000 nodes around this one which best, which best capture its community, or one of the communities it's in. There are many overlapping communities. So when we want to do that, we don't want to ever look at the trillion nodes. So you say linear time algorithms are actually very bad for us in this setup. We want to look locally. And this is a problem that sounds like something which can only be analyzed heuristically. How are you ever going to do something rigorous for this setting? But surprisingly, Spielman and Teng made this into a rigorous theory using random walk ideas. And what we're doing is developing from their work. So I'll say more later, but just to give more examples, here is one important bipartite graph is the one that connects advertisers who go advertise on a search engine to keywords that they're bidding for. And so we have an edge when an advertiser wants to bid on some keyword. And this bipartite graph, again, is interesting to partition for the purpose of identifying kind of topics of advertisements. And now the local partitioning, as I mentioned, is different from the global in that we're not going to try to partition or even look at the whole graph. And we can, in global partitioning, one possibility is to use the local as a subroutine and keep slicing off pieces. That's not going to be the main application. So how do we evaluate the local partitioning algorithm? So we're going to have some starting node V and a target conductance phi, where we're going to aim for finding something with this conductance. And our goal is to find some set S with a small amount of work or complexity. And what we'd like is that the work be small compared to the volume of the set. So we don't want really the work to depend or to strongly depend on the huge graph, more on the size of the community we're going to find in the end. So this is our goal, to bind this, and maybe as a function of the target conductance. So this would be a goal. We can't quite achieve that. You see, there is some logarithmic dependence on the size of the big graph. And now the algorithm will have a local approximation guarantee if so maybe I'll emphasize this last point. So suppose we know there is a piece, there is a community with conductance phi. Actually finding the graph or the set with the minimal conductance is an NP-hard problem. We're not going to try to find the optimal. The idea is, though, that if there is a very good cut, we should be able to find a reasonably good cut quickly. So we're not guaranteeing to find the optimal cut. We want an algorithm that hopefully many times will find the optimal cut, but will have a theoretical guarantee that if the vertex has a set around it with a really superb cut, then we'll find a pretty good cut around it. So we want a theoretical guarantee of some minimal performance and then hope that on average it will perform better. And there's some history of the kind of guarantees that were obtained. As I said, the pioneering work on this was done by Spielman and Teng in 2004. They used a algorithm based on random walk. So you can think of, you analyze the distribution of a random walk starting at your node, and whenever the probabilities become too small, you just truncate them to 0. And if you do this, tuning the parameters correctly, you get an approximation like that. And so the work volume ratio, as you see, it's some negative power of this conductance phi, and then you have the approximation guarantee. So you'd like both of these to be as small as possible. And here, since phi is a small number, tending to 0, phi to the half is better than phi to the 1/3, which was in the original algorithm. So the best random walk-based algorithm and algorithm we have are very close in performance, but the one we have has the advantage of having no parameters to tune, as we'll see in a moment. It is very straightforward to run, and it has a natural meaning that I'll show as well. Okay, and it can be used to find balance cuts, but I'm going to skip this application. And I want to tell you what the algorithm is based on. So it's based on this evolving set process, which in this form was developed in joint work with Ben Morris in Annals of Applied Probability, where the focus is on bounding mixing rates of Markov chains, but it's actually closely related to earlier work on strong stationary duals by Diaconis and Phil. So what is this evolving set process? One intuitive way to think about it, it's a smarter version of breadth first search. Suppose you have a node, say, a person on Facebook, and you want to find who his friends are. So you can look at his list of friends, and then you want to find the second order friends, and you get a bigger list. And if you repeat this a few times, you'll get a huge number. But these second order friends are not all alike. Some of them have many much stronger connections in the sense that they have many more common friends with the person we started with. So how can we do this in a more intelligent way? And that's one thing the evolving set process captures. So how is this doing? So first, we want to, in order to we're going to think of an underlying Markov chain, which would be the lazy random walk. So with probability half, you stay in place. With probability half, you go uniformly to one of your neighbors. And then with that Markov chain in mind, we can give a weight to every node, whether it's inside or outside the current set. So suppose I have now a current set S. I check for every vertex what fraction of its neighbors are in S, but keeping in mind that half the weight of the neighbors is on the vertex itself. So if I look at this vertex C, it has 4 neighbors, so we have probability, and 2 are inside and 2 are outside. So if we just would do simple random walk with probability half, we jump outside. But since we're doing lazy random walk, we jump outside only with probability a quarter. With probability 3/4, we stay inside. So 6/8, we stay inside. With this vertex B, with probability 3/8, we move inside, okay? Because we're doing a lazy random walk. Is the rules clear? So this is the underlying Markov chain. Now we make from that a set-valued Markov chain, which is going to evolve as follows. So for every node, we will put it into the set in the next round with the probability, which is this fraction of its neighbors in the set in the current round. Okay, we have S. We look for every vertex, what fraction of its neighbors are in S, keeping in mind that half the weight is on the vertex itself, and then we put it in with that probability. So here, if this is the current set S, in the next step, B will be inside S prime, the set in the next step, with probability 3/8. C will be inside the probability 6/8, and so on. Just the probability that in the step of a lazy random walk, they will be in the set, yes?
Can you explain this, the probability CS again? There are 2 going inside. And
2 inside, 2 outside. But remember, we're doing lazy random walk, right? So with probability half, we're staying in place.
Right.
So what is the probability we're going to go outside?
Right.
2/8. Okay?
Plus that one.
The probability will go outside is 2/8. The probability will stay inside is 6/8. So that's okay. So the way the set is going to evolve is every vertex will be in the set in the next step with probability that a lazy random walk will put it in the set. Now I told you these probabilities, but of course to really define the next set, I have to define the joint distribution. And this is not going to be, these decisions are should not be made independently, but in somehow the most correlated way possible, which is done by picking a uniform threshold, and you just put in, so suppose I'm now at S0, at the set S1 in the next step, we put every node with probability, which is this, essentially the fraction of its neighbors in S0. So we put a node Y inside if this probability exceeds the uniform threshold U, and we pick one threshold U for all the nodes. So we don't pick a separate one. And each round we pick just one u. Of course, in the next round we will pick a new independent uniform variable. But in each round there's just one variable. This ensures that these decisions are made in the most correlated way possible, which will make the set move as fast as possible, which is our goal here. Okay. So the way I define the Markov chain here, the empty set and the whole space are absorbing states. If I'm, the empty sets, nothing can come in. If I'm in the full space, nothing can go out. So what we will in the end want to run is a conditioned version of this, or a Dept transform of this process, where we take it and condition it to not vanish, so to get absorbed in the whole space. There's a delicate point here. We're not, in running the algorithm, we don't actually want to run it till it gets absorbed in the whole space, but we want to avoid this kind of disappearance, so if we start with one node, then this process is very likely to disappear right away, to just go to the empty set. So we're going to make sure it doesn't do it.
So you're not doing that by controlling U. U is always uniform.
However, then there's a question, how do you implement this conditioning? And the conditioning is implemented by controlling U. So, but the formal kind of probabilistic description is you have this process, and then you condition it not to get absorbed in the empty set.
And this U is fixed once and for all, or do you
No,
change
it's fixed for each round. It's
for
fixed.
each?
Every round it's fresh, independent choice. But for each round, the decisions for all the different nodes are made with a single U. Yes?
Maybe you said this. Why is it important for you to be random?
Well, again, I want for you to be random. So I want to put in vertices. So every vertex I want to put in with a probability which is a fraction of its neighbors. But you're asking, maybe I could just set a fixed threshold and just put in things like that. That is exactly a method that might perform well in some initial steps, but then get stuck. And the randomness allows the process to get unstuck from and reverse kind of bad choices that it made earlier. So,
But it could also prevent a good choice, right?
it can also prevent a good choice, but so you may want to run this algorithm several times from the same initial condition until and also when you run it, you keep track of what kind of sets it has found along the way, and you take the best one, not necessarily the one it ends up with. So it's the best one along the way. But in particular, if you didn't use randomness, then trying again would not help. So in implementing this, you would often want to do multiple runs of the algorithm. So coming back to Andre's question, what about controlling U? How do you implement it? So there's a beautiful coupling idea in the paper of Diaconis Phil, which can be used here to implement this process. Maybe I'll say there's more about it later in the slides, but I'll just say something now. One way to make the set, the evolving set, stay non-empty is to fix a node, say the starting node, and insist that this node stays in the set. However, that turns out to be not give the right distribution. Surprisingly, the following does give the right distribution. Start a random walk using the lazy random walk. Start a random walk from the initial node and insist that this moving particle always stays in the set. So how can you insist on that? We're picking a uniform value U, and this if this threshold U is too high, it might make this moving point, get out of the set. So we pick U, instead of picking U in the interval 0, 1, we pick it in 0 times exactly this ratio, but for the moving particle. And it turns out if we do that, we exactly accomplish the Dept transform, or the conditioned process that is the evolving set process conditioned to absorb in the whole space. This shouldn't be obvious. So, but this is kind of a preview of how one really implements this process. However, it's useful to keep in mind also the original unconditioned process because, to quote something Shankar said at lunch today, in every problem, the key thing is to find where is the martingale, and so that's also the key here. So if we look at the original unconditioned evolving set process, then the volume of the set, which I remind you it's a total, the sum of the degrees of the vertices in the set, this volume turns out to be a martingale, which again, this is actually very easy to verify. But it also tells you that if you start in a singleton, then it's really very likely to be absorbed in the empty set rather than in the whole space. So the conditioning is going to be really important, unless otherwise your set is just going to vanish right away. But this is kind of crucial in the analysis of the algorithm. And there's also a connection with the random walk. Namely, suppose I want to know what is the probability at time t that the vertex y is in the set. So this is exactly the transition probability from x to y, just with a factor of the degrees. But maybe think of a regular graph where all the degrees are the same. Then the probability, when you start at a singleton x, the probability that y is in the set at time t is exactly the transition probability for the walk. So again, this is actually easy to verify by induction, but is crucial in the analysis. And then this is what I told you of how you implement this process. So we start with a set which is x0 and a moving particle which is x0. First we move the particle according to the walk. So this is, the particle ignores the set, but the set will respect the particle. So the xt plus 1 just moves to according to the transition probability, it's the lazy random walk. Then we update the set. So suppose we're now at the set S, we're going to pick a threshold U, but not in 0, 1, rather uniformly in 0 times p of x prime S. And this turns out to be exactly what the doctor ordered in order for the process to implement this Doob transform that we were aiming for. And again, this fact was first discovered by Diaconis and Phil with very different notation. So even the connection was not obvious, but really this coupling is due to them. Yes?
Is it obvious that your U doesn't get too small, so you get the whole V?
Again, so first of all, most of the graphs we're interested in, the neighbors of every vertex is very small compared to the whole graph. So, so even if U is 0, then what you will do is you'll grow to, you'll grow to all the neighbors of the current set, which is still far from the whole graph. Okay. But suppose this happened once. So suppose then you would indiscriminately take all the neighbors of the current set into the next set. But then, in the next round, if U is small, then bad choices will be rejected. Because if a vertex kind of was taken in the previous round, because you chose a very small U, but actually has very few connections to the rest of the vertices in the set, then in the future round, it's likely to be ejected. So this process has some self-correction built in. So it occasionally tries to venture into new territory, but if that territory is not well connected to the previous one, it will just reject that. So maybe we can quickly go back to the simulation. So in this graph, which again is rather small compared to those we really want to run, so this is an implementation of this process. So again, this graph is very small. So in this case, the set will swallow the whole graph in a short time. We want the algorithm to be fast enough so on such tiny graphs it will finish them very quickly. But when this is run on a graph of 1 trillion nodes, it's not going to swallow the whole graph very quickly. So, but what you can see is at any time, most times the set you have has relatively small boundary, because that's because of the rules of how it's constructed. Yes?
Is it possible that you have like a set from the starting point, you have a set of P's that are like, they have order of, the P starting point and P the next one. So they form kind of a serial inequality of P values, P's, not P values.
You mean the U's will be, or the P's?
I mean, the U.
So, of course, the U's are picked at random, so you could be lucky or unlucky with the sequence of U's. So the U's are the thresholds that you pick. Okay, maybe I will come back to that in the end.
So question.
Yes.
So I thought the idea was to stop once you get a set.
Absolutely. You
So
stop.
This
So
is continuing forever.
this is continuing, but in reality, you have a fixed budget of time. So when you run this, you have a target conductance, and you also have a budget of time that you're going to run. So what you do, so the algorithm, as it runs, it actually keeps track of what's the conductance of the current set, and if it reaches the target, it stops. If it times out, then it knows what is the best it's found along the way, and if necessary, you try again and run the process again. Each run is different from the other one, previous one. Yes.
I'm still a little confused. You said that your transform is that you condition of not being empty in the whole space.
You condition not being empty, so it means
okay.
yes, condition. It means you do converge in the limit to the whole space. Absolutely, probability 1. Again, the algorithm, when actually implemented on a large graph, you'll always stop it way before it gets to the whole space. So really, the effect of the conditioning is just to avoid the vanishing. But if you do run it till the bitter end, it will swallow the whole
I
space.
understand. I misunderstood your condition.
Question?
Yes.
In practice, as you're tracking, as the sets are growing, you're
Yes.
tracking the conductance.
Yes.
Is there sort of a characteristic behavior in which you expect the conductance at some point to sort of drop off, and you can say empirically maybe with certain types of...
Well, it really depends. It really depends on your graph. So, okay. So there are separate things like how this performs in practice on graphs of interest, and what kind of guarantees you can give on all graphs. So of course there's a test of practice you can implement, but what's surprising and gratifying to me is that you can give some theoretical guarantees valid for all graphs. And so because this is because this is a martingale, the probability, the original evolving set process is a martingale, so the probability it gets swallowed in the whole space is just the volume of the initial set. Because the volume is a martingale, then so if I take so I should say this is, so the probability it gets in the whole space is the volume of the initial set divided by the volume of the whole space. This is good, and once you know that, then the transition rule for the Dept transform is just given by a ratio of volumes. So you can, this is a new transition kernel from a set S to S prime. If K is the transition rule for the evolving set process I told you before, then you just bias it by a ratio of volumes. This is how you implement Dept transform. And once you know that, there are some consequences on calculating expectations with respect to this. And here are some examples of the process, how it's run. And then there are some theoretical guarantees on the performance. So here is how some rules on how to run it. So you stop if either you ran out of time or if you reached the conductance below some threshold. And here we set, turns out to be some threshold that is likely to be reached. And when you do that, you get bounds on the expected work you're going to do and on the success probability. So again, this algorithm is not at all guaranteed to succeed, but we have some lower bound of success probability, so if you iterate enough times, you have some assurance of high probability of success. So this is just some example, and in this lecture I won't go into the details of the proof, but the paper is available on the archive if you want to dive into it. It was really kind of an enjoyable tour into martingale theory for us. But so I'm going to actually skip the details of this proof and say something about where the improvement in the runtime comes compared to other algorithms, which is an important point. So other algorithms maintain some transition probability matrix. So you have your initial node, and you maintain weights on all the other nodes, which tell you, how good they are. Now, so this is roughly the transition matrix of a random walk, but truncating small values. Now, when you want to move the transition matrix one step forward, you have to update all these, the weights on all these nodes, which can be time consuming if your set is already pretty large. The evolving set process, instead of keeping weights, it keeps a random set. So it's really a random 0-1 valued function. And the updates you have to make are only on the boundary of the set. Because things that are strictly on the inside, they're going to be on the inside the next step. Things that are strictly on the outside, they have to stay on the outside the next step. So the updates only happen along the boundary. And here we have a very fortunate dichotomy. If the boundary is small, then, we just have to make a small update. If the boundary is large, then this implies that the process is moving very fast, because the